Welcome back to this course of crystallography. In the previous class, we have learnt about how to construct a reciprocal lattice and how to get the reciprocal lattice drawn for orthorhombic and monoclinic systems, and we have learned about some relationship of Bragg's law in reciprocal space. And then we discussed about the possibility of some systematic absences. We have shown you an animation where we could see that some of the reflections were bright and some of the reflections were dull, and they were not, some of the reciprocal lattice were dull and they were not making any diffraction when they were crossing the Ewald sphere. So we have discussed about the systematic absence arising out of various lattice centerings, and we would like to continue from here. The translational symmetry elements other than the unit translation, for example the lattice centering, glide planes and screw axis, they result into systematic absence conditions for a particular set of HKL reflection. So when we are trying to see the reflections which are corresponding to the symmetry element, which is a B glide or a C glide or N glide or a D glide, which can be perpendicular to A, what could be the systematic absence condition? To understand that, we first need to see against which axis the glide is perpendicular. So when it is perpendicular to A, the Miller indices for the planes which may suffer systematic absence should be 0 KL. So this 0 comes when it is perpendicular to A. When it is perpendicular to B, it is 0 for K, and when it is perpendicular to C, 0 comes for the L index. At the moment, this you may need to memorize because we have not understood how these systematic absence conditions can be derived, but the easier way to remember is this. So when a plane is perpendicular to A, the H index is 0. When a plane is perpendicular to B, the K index is 0. When a plane is perpendicular to C, the L index is 0, and this set of reflections suffer systematic absences under certain conditions. So now when I am saying it is a B glide, that means the translation is along B. So now when we look at this particular reflection, which is a set of 0 KL reflection, and I am saying that it is a B glide, that means the translation takes place along B. So the index which corresponds to B, when it is odd, the set of reflections are said to be systematically absent. In the same manner, when it is a C glide, which means we are talking about a translation along C, immediately the set of 0 KL reflections with L equal to 2n plus 1, so n equal to odd, becomes systematically absent. In the same manner, when we say it is N glide and perpendicular to A, that means the translation happens simultaneously along A and simultaneously along B and C. So in that case, the sum of the indices K plus L is going to be odd, and those reflections are going to be absent. What does it mean? In case of 0 KL set of reflections where 0, 1, 0, 0, 3, 0, etc., or 0, 1, 2, 0, 1, 1, all these will be absent for a B glide perpendicular to A. Similarly, 0, 0, 1, 0, 0, 3, 0, 2, 1, 0, 2, 3, etc. will be absent in case of C glide perpendicular to A. And N glide, when the sum is odd, the sum of K plus L is odd, then it will be absent. In the same manner, when we talk about a D glide, the systematic absence condition is K plus L equal to 4n plus 1, 2 or 3, which once again indicates that the sum is odd. So in the same way, one can understand the corresponding A, C, D and N glide perpendicular to B and C, which I am not going to explain in this lecture. In the same manner, when we have a screw axis, it can be a 2-1 screw, 3-1 screw or whatever, any kind of screw axis which is parallel to A, B or C can give rise to systematic absence conditions. So in this case, if we are talking about a screw axis which is parallel to A, then the reflections that get hampered are set of H00 reflections. So here one should remember that when I am saying a screw axis, it is parallel to one axis, either A, B or C. If it is parallel to A, then the H index remains, K and L becomes 0 because you are doing a rotation like that, which is in the K and L plane, and the reflections and the planes and the reciprocal lattice points with 0 K and 0 L will fall in this particular row. So in that case, the H equal to 2n plus 1 is the condition for systematic absence. In the same way, for 2-1 screw parallel to B, K is odd, and a 2-1 screw parallel to C, L is odd, and in the same manner, the higher n-fold screw axis like 3-1 and 3-2, 6-2 and 6-4, 4-1 and 4-3 are understood in same manner, and here again 6-1 and 6-5. So this is how one can understand the systematic absences that might appear due to different types of non-lattice translational symmetry. That means it is not unit translation. These translational symmetries are half translation, be it a lattice centering or be it a screw axis or a glide plane. These are the ones which generate the systematic absent reflections in a given crystal structure. So with this initial background on theory of X-ray diffraction, I would like to change the topic now, and we would like to discuss about the crystal growth, the mechanism of crystal growth, and how one can grow good quality single crystals, what do we mean by good quality single crystal and things like that, with some figures and diagrams. So now we would like to discuss the crystallization methods and selection of suitable single crystals for X-ray diffraction. The method of crystallization means we are trying to bring a set of atoms, group of ions or a group of molecules from its randomly arranged state in either liquid or in gaseous phase to a particularly ordered and three-dimensionally translational symmetry followed with other symmetries incorporated into a network of a solid state. As you know, one can only crystallize compounds in 230 different ways to generate 230 different space groups. This ordering is very crucial when you start from a gas phase or a liquid state of any particular compound. So the method of crystallization takes place through two very simple but highly complicated methods processes called nucleation and growth. Crystallization is a dynamic equilibrium of ions, atoms and molecules between a liquid or a solution state and a solid phase. So what we have is a set of atoms or ions or molecules in solution and is in equilibrium with the same in solid state. And when this equilibrium shifts more towards the right, then we end up getting the crystal growth. What happens here is that these atoms, ions or molecules try to come together. They start interacting, they start talking to each other using various intermolecular interactions or interionic interactions. These interactions can be ionic in nature, this can be covalent in nature, this can be non-covalent interactions like hydrogen bonding, etc. So what can happen is a set of molecules can come closer and form some interaction pair in solution. And you remember, in solution, these atoms, ions or molecules are always in random motion. So this group will again break and they will be scattered here and there due to their random motion. So this process continues, and what happens is if we try to allow the solvent to evaporate or we try to lower the temperature, in either case we are trying to increase the concentration of the solute particles in the solution that we want to crystallize. So in this process, what happens is that a critical size is achieved with these molecules or ions, which then can arrange in appropriate order to form a very, very tiny crystalline nuclei. And this crystal nuclei, when reaches a critical size, it starts to grow, and then we end up getting a significantly large crystals. When we are talking about large crystals, we are talking about crystals of size larger than 50 micron, and it can be anything larger than that. So the rate of crystal growth depends on various factors like the concentration, the media of crystallization, and the temperature of crystallization. So higher the concentration of solute, faster is the crystallization process. Depending on what kind of media we have, how these atoms, ions or groups of atoms or molecules interact with the media. Here we mean by media as the solvents or solvent systems, which can form different types of intermolecular interactions with our target molecules or atoms or ions and control the crystallization process. Temperature has very important role in crystallization. Some compounds crystallize at higher temperature, some compounds give you very nice good crystals at a much low temperature like -15, -20 degrees centigrade or even lower. So we will discuss about some of these crystallization methods in the following slides. The surface of crystals which holds the molecules and ions very firmly are most effective surfaces for crystal growth. So not every surface of crystal grows evenly. Some crystal surface grows much faster than the other surface that can be seen under a microscope. The physical shape of the crystals grown are called the crystal habit, which means a compound can crystallize in different shapes, different geometric shapes. Crystals can be like prisms, can be like plates, rods, needles, and so on. So that shape in which a compound crystallizes is called its habit. In general, when we deal with different types of materials in the lab, we have different methods to apply for different types of compounds that we encounter in the lab. In general, in most of the labs, we encounter different types of organic and soluble inorganic materials which can be crystallized using a particular type of methods. In some cases, we are trying to generate insoluble inorganic ceramic materials or materials which can be crystallized from a solution, but then the compound form does not dissolve in any solvent. And then we can try to crystallize materials which are liquids or gases at ambient conditions. So let us one by one see how these different types of materials can be crystallized. So to discuss at the beginning, let us consider the crystallization of organic and soluble inorganic materials. Mostly there are 4 to 5 different ways one can crystallize these materials. You will see here in all the cases we have a slow evaporation or a slow cooling. Why do we need to make the process slow? Because we would not want to disturb the system very frequently. We would like them to crystallize as naturally as possible, and we do not want the system to be hurried up for crystal growth. So when we are trying to crystallize from a pure solvent, we need to keep few things in mind. We first need to know what compound we are dealing with. We need to know in what solvent we have high solubility, and in which type of solvent we have low solubility, and in what kind of solvent it is insoluble. Depending on the behavior of the target molecule and the interaction with different types of solvents, one compound may like a protic solvent, one compound may like a aprotic solvent, some molecules may want solvents which can form strong hydrogen bonds, some molecules which may like molecules like carbon tetrachloride and so on. So we need to know the solubility of our compound in different solvents. So in that, what we try to do is we try to make a saturated solution in a small crystallization vessel, like we try to use a very small crystallization beaker, maybe a 5 ml beaker. So in that we take 10 to 15 mg of the product if that is soluble in about 2 ml of solvent. So what we are trying to do is we are trying to make a very concentrated solution of the solute in the given solvent in which it dissolves very nicely, and then we cover the top of this beaker with a paraffin film and we make a few holes. We make a few holes, very tiny holes with needles on the cover, and allow the solvent to evaporate at a very slow rate, and then we try to keep this beaker in a refrigerator at about either 4 degrees centigrade or at about minus 15 degrees centigrade, so that the solvent which is inside evaporates very slowly over a period of 7 to 10 days. So on doing this process, what happens is that with slow evaporation of solvent at a given point of time, the solution reaches saturation with the compound, and then the compound slowly comes out of the solvent, the nuclei starts to grow, and we, at the end of the day, maybe after a week or so, we end up getting crystals of the compound sticking on the walls. This method works for a large number of different compounds where a single solvent is good enough for crystallizing these compounds. But there may be situations of difficulty. It may so happen that from a particular solvent we may not end up getting a single crystal, but we may end up getting a polycrystalline powder being deposited from the solution. So in that case, what we need to do is we use a mixture of solvents, generally a mixture of solvent plus anti-solvent, means a liquid in which your compound does not dissolve. So we take a liquid, maybe suppose dichloromethane, in which the compound dissolves completely, and cyclohexane or N-hexane, in which the compound does not dissolve at all. So we first dissolve the compound in a solvent in the same manner as we have done it previously, and then we add the anti-solvent in the same solution and mix them well. So what we now have is a solution of our compound in a beaker in two different solvents. So now what will happen is, when this solvent system would slowly evaporate at about 4 degrees centigrade or at minus 15 degrees centigrade in a freezer, this slow evaporation process will then be controlled by the rate of evaporations of the solvent and anti-solvent, and a phase equilibrium will be reached, and under that condition, when the solvent is much less in amount and your solute cannot stay in the solvent, it then starts to grow its crystal, and there may be some amount of anti-solvent still left over, in which those crystals will be floating, and it will be easy to collect those crystals from this particular disolvent mixture. It may so happen that the two solvents that we have used, of course not in case of dichloromethane and hexane, it may be in case of methanol and THF, it can be methanol and dichloromethane or some other combination, where the two solvents also interact with each other, form some kind of weak hydrogen bond, and then crystallize along with your compound and form a solvate of that, which was not possible when we used a single solvent and we could not crystallize it efficiently. The third method that one can use is called a vapor diffusion method. In this, once again we need to use two different solvents. What we do is that we take a smaller beaker, in that we take a test tube filled with a solution of the desired compound, in a solvent in which the compound dissolves most, and then we add a second solvent in the outer beaker, in which the compound does not dissolve. Solvent 2, in which the compound does not dissolve. Then if we isolate the entire system in a closed container, maybe in we place it in a larger beaker and cover the top with paraffin film completely and do not allow any hole so that the solvent mixture does not evaporate. We can fill the outer part of this larger beaker also with the solvent 2, so that there is an excess of vapor of solvent 2 inside the enclosed container, and though that vapor can then slowly diffuse into the test tube in which we have our compound dissolved in the desired solvent. So in this process, the vapor of this anti-solvent can diffuse through a vapor state to the solution in which we have our target solute, and in the same process simultaneously the solvent which is inside the test tube will evaporate and slowly come out and fill the outer aerial volume of that container and slowly reduce in volume. So by this vapor diffusion method, the diffusion of vapor of solvent 1 in solvent 2 and solvent 2 in solvent 1 may result into a good quality single crystal growth. This method is many times useful in case of organic compounds. In chemistry teaching laboratories, when we try to make some derivatives, we must have learned how to purify those derivatives by crystallization method. So all of you might have done in your undergraduate courses where you have made some particular compound from a starting material and your teacher has asked you to crystallize from a solution. What you might have done is you might have made a saturated solution of the compound in a test tube by slowly or rapidly evaporating the solvent and making it saturated at elevated temperature, maybe at 60 to 70 degrees centigrade, and then you might have left it on the rack, so standing at room temperature, which is about 30 degrees centigrade, for about 1 hour. In this 1 hour time, the saturated solution has cooled from about 60 to 70 degrees centigrade to about 30 degrees centigrade. So this is a method of cooling, of course uncontrolled, but it is a method of slow cooling. You are not applying any coolant to cool the substance. You are allowing the solution to radiate its heat slowly, and as a result of lowering the temperature of a saturated solution, as we know, the solubility decreases drastically and we end up getting crystals of the compound in that test tube or a beaker. One of the recently applied methods of crystallization is in the presence of external stimuli. These external stimuli can be of different types. These external stimuli can be a compound. The crystals of a compound which does not dissolve in your crystallization solution can be dropped in the solution as a surface on which the crystallization can take place. Otherwise, the crystals may not be growing. The external stimuli can be laser beam. Recently, there are reports where a solution which is being irradiated with a given laser of a particular wavelength generates a local heating, and on withdrawal of that local heating, the crystal growth starts. Crystallization can happen in presence of some magnetic field or electric field. This type of crystallizations are done in case of materials which are magnetic in nature or they have some electric dipole moments which gets arranged in a very high electric or magnetic field, and then those compounds can crystallize. So in today's lecture, we have initially learnt about the systematic absences and now to understand those systematic absence conditions, and then we have discussed about various methods of crystallization of organic and inorganic soluble materials which can be dissolved in a solvent or a mixture of solvents, and then these can be crystallized. So we will continue this in the next lecture.